All right, well, welcome back. So in the last video, we had a look at some practice problems of strategies of integration. We had a look at some exercises as well up here. So I provided 5 examples of what to integrate using the techniques of integration and what kind of integration you should be using. So we had a look at these 5 examples. And so that's basically what 3.6 was about. Basically just to get you to know what technique to actually use whenever you're integrating. So this lesson, we will be focusing more on a new concept or another concept of integration, which is called the improper integrals. Okay, so let's say that first of all, we are able to find areas under the graphs that are continuous on an interval. So for example, if we have a graph that looks something like this, we're able to determine its area under a region from A to B. So this is by determining the definite integral of the function. But in some cases, we want to determine the area under the graphs where there are continuity or discontinuities and where the function is actually not bounded at that area. So for example, if we consider the graph of y is equal to 1 over x squared, so if we consider the graph, I'll try to graph this. Okay, so it looks something like this. So between A to B, so here's A, and so we're able to determine the area that is between a certain interval A to B. So this is what we could actually determine. But suppose there was no B here. And instead, this just gets filled completely by A. So the area just keeps on going towards infinity, right? So suppose we want to find the area to the right of A. So we want to find out what happens as it approaches infinity. So we know that the area from A to B of 1 over x squared dx. So if you compute this integral, you should get negative 1 over x from A to B. So that'd be negative 1 over b plus 1 over a. Now, let's see what happens by taking the limit of the integral as b approaches infinity. So we're technically taking the b here still, but it's approaching infinity. So this b value could just keep on going. So as the limit, so we're saying that, well, the limit as b approaches infinity of this integral of a to b of 1 over x squared dx, which we have already calculated. So we only want just the limit that involves b. So as b approaches infinity of negative 1 over b plus 1 over a. Well, as b approaches infinity, this actually just goes to 0 because it's a rational function. So it would just be equal to 1 over a, which is actually the area under 1 over x squared from a to infinity. So in other words, we could actually write this as the integral from a to infinity of 1 over x squared dx. And we compute this, this is just going to equal to 1 over a. So that's our goal in this lesson. We want to try to evaluate some infinite integrals or regions that are actually at infinity rather than just at a finite b value. Okay, so what is the area to the right of x equals to 1 or x equals to 2? So to the right of 1 and to the right of 2, well, over here, if we say a was equal to 1, as 1 approaches in 1 to infinity then, well, that'd just be 1 to infinity. 1 divided by x squared dx. Since we already found the integral, which was 1 over a, this would just equal to 1. Okay, but what about 2 then? Well, the integral from 2 to infinity, then we would just have 1 over x squared dx, but this is equal to 1/2 then, according to the integral that we have actually computed. Okay, but let's see what happens. So what is the area under the graph of y is equal to 1 over x? So to the right of x equals to 1. So we integrate from 1 to infinity of 1 over x dx, but we have to let some parameter t, and as we take the limit of t to infinity, of the infinite 1 to t of 1 over x dx. So this is the purpose of having this limit here, so that we are able to calculate the limit as t approaches infinity, rather than what exactly happens at infinity. So we would still have the limit as t approaches infinity. The integral inside would just be the ln of x from 1 to t. So we only need to focus on what happens with the ln of t. So t approaches infinity of ln of t and minus the ln of 1, which actually equals to 0. So we see here, as t approaches infinity, well, if you try to sketch the graph of this, it would look something like this. So as it approaches infinity, we see that the integral actually diverges, or the limit actually does not exist. So this, we say it does not exist. So we say that the limit, or the improper integrals, are said to be convergent. So convergent is a keyword if the limit exists. So for example, if this were to have some finite value, then we say that the integral is convergent. For example, as well, if this integral we say it's convergent, then the limit actually exists. But we also say that the integral is divergent if the limit does not exist. So in fact, from this part over here, we see that the limit does not exist because as t approaches infinity, the ln of absolute value of t is approaching infinity, which means that the limit does not exist. All right, so that leads us to the improper integrals of type 1. So this is called the type 1 improper integral. We say that there are 3 different cases. So the first one being that if the integral of a to t of f of x dx exists for every number t greater than a, then we say that the integral from a to infinity of f of x dx is equal to the limit as t approaches infinity from a to t of f of x dx, provided that this limit exists. So this finite number is a pretty important fact. So that way we could say that the integral converges. If not, diverges, meaning that it also does not exist. All right. And the second case is, if we have the integral from t to b of f of x dx, so it's going to be from the left now, exists for every number t less than or equal to b, then we say that the integral from negative infinity to b of f of x dx is equal to the limit as t approaches negative infinity of the integral of t to b of f of x dx, provided that the limit exists. So that's also another key fact here. So if this limit does not exist, this integral, this value does not exist, so we say that it diverges. So one more case, if both the integral from a to infinity of f of x dx and the integral from negative infinity to a f of x are convergent, then we define this expression here. So we say that the integral from negative infinity to infinity of fx dx to be the sum of these two integrals. So they would say if both of these are convergent, then this would also be convergent in the end, right? So let's have a look at some examples. So the first example is asking us to evaluate the following integrals. So for part A, we have the integral of e to the power negative x from 2 to infinity. So this integral isn't too bad to compute. So let's go ahead. So remember the limit. We say that the integral converges or exists if the value of the limit is finite. So we say that the limit as t approaches infinity of the integral from 2 to infinity of e to the power negative x dx. Or this should actually be t here, right? Okay, so now we say that, well, the limit, if we evaluate this integral, as t approaches infinity, of negative e negative x from 2 to t. So we are only interested as t approaches infinity for the first term, so we could just say that the limit as t approaches infinity of negative e negative t, and then minus e to the power negative 2. Well, what happens as t approaches infinity is, so if we try to visualize the graph of this, it would look something like this. So this is the graph of e to the power negative t, or the negative version. So we see that as t approaches infinity here, this value is actually going to go to 0. So because it's equal to 0, we would just have, this should be a plus. So that means e to the power negative 2 is the finite value. So we see that the limit exists. Okay, so let's have a look at the second one. So we have here the integral from negative infinity to infinity of 1 divided by 1 plus x squared of dx. So this is actually one of the integrals that we had a look before. So if you remember that the integral or the antiderivative of 1 divided by a squared plus x squared dx was actually equal to 1 over a tan inverse x divided by a plus c. So let's go ahead and put that in. So we know that this integral is indeed, well, if a is equal to 1, we would just have this, but with equal to 1. So, but let's pick a point here. So let's say we let a pick 0, for example. So meaning that, well, because the function here is actually symmetric, we could actually separate them into two parts. So let's say from negative infinity to 0 of 1 divided by 1 plus x squared plus the integral from 0 to infinity of 1 divided by 1 plus x squared dx. So what this graph actually looks like is, if you consider this as a rational function, it would look something like that. So because it's also symmetric, we could actually go ahead and just combine these two. Because it's an even function, so then we could also say, well, 2 times the integral from 0 to infinity of 1 divided by 1 plus x squared dx. And so that's equal to 2 times the tan inverse of x evaluated from 0 to infinity. So so let me write down the limit. So 2 times the limit as t approaches infinity of tan inverse of t, and then tan of 0 tan inverse of 0 is just going to be 0, so we don't have to worry about that. This value is actually going to be approaching towards pi over 2 because the graph of tan inverse looks something like this. And there are two horizontal asymptotes at pi over 2 and negative pi over 2. So that means as it's approaching infinity, it's going to be approaching towards pi over 2. So that means we would just have 2 times pi over 2, which equals to just pi. So that means the limit exists, so the integral here actually converges. Okay, so let's have a look at the third one where we have sine of x. The integral from 0 to infinity of sine of x. So the integral of this simply just becomes, so the limit as t approaches infinity of the integral from 0 to t of sine x dx, which then becomes the limit as t approaches infinity of the negative cos of t x evaluated from 0 to infinity t. So that means as t approaches infinity though, so this is just equal to negative limit t approaches infinity of cos of t plus cos of 0, so that's equal to 1. But this integral here, or this limit here, does not exist. Because the cosine function can only go either to 1 or negative 1. So we cannot make any conclusions of this. So this limit does not exist. So we say that the integral from 0 to infinity sine x diverges because there is no limit. Okay. So the last one is as follows. So we have the integral from negative infinity to 0 of 1 divided by the square root of 1 minus x. So for this one, we still use the same notation. So say the limit as t approaches, let's do negative infinity. So we have the integral of t to 0, 1 divided by the root of 1 minus x dx. So if you calculate this integral, what you should actually get is so we had the limit as t approaches infinity. The antiderivative here should just be negative 2 times the square root of 1 minus x. So we're ranging from t to 0. Well, as if we put 0 in, should be no problem. We would just have negative 2 times 1 minus 0. So that integral, or the value limit, exists. However, for the second one, we have the limit as t approaches negative infinity of 2 multiplied by 1 minus t. But as t approaches negative infinity, this is going to become a positive number, but it's going to get larger. And it does not converge to anything. So this value over here does not exist. So we say that this integral from negative infinity to 0 of 1 minus x squared, or 1 minus x dx, diverges. So that's an important concept to know about. Okay. So now let's try to do a couple of observations here. So let's see what happens when we have the integral from 1 to infinity of 1 divided by x to the p. So we want to find out what values of p will make this integral actually converge. So let's start with the cases. So let's say what happens when p is equal to 1. So when p is equal to 1, then we would just have this integral. The integral from 1 to infinity of 1 divided by x of dx. But this is just going to be the ln of x from 1 to infinity, or if you want to, this is also saying the limit t approaches infinity of the ln of x from 1 to t. So we see that as t approaches infinity, the value here actually diverges. So as t approaches infinity, for p is equal to 1, integral 1 infinity x dx diverges. Okay, so that's one case. But what about if we consider the values that are not equal to 1? So let's say for when p is not equal to 1. So that's just going to be the standard integral then. So we just have the integral from 1 to infinity. I'm going to write this as x to the power negative p of d of x. And then this integral would just be 1 divided by negative p plus 1 times the x to the power negative p plus 1 from 1 to infinity. Now there are some special cases that we need to put here. When p is less than 1, so consider when p is less than 1, then that means the exponent here is going to be positive. So that means negative p plus 1 is greater than 0. And what happens when the exponent is positive then? So for example, say x squared. Well, if that was the case, the integral here would actually diverge. So we say that the integral diverges. X to the power negative p dx diverges because this is a positive value now, because if it's positive, then it diverges. For example, take x squared. Okay, so we had this part. Now, what about when p is greater than 1? So when p is greater than 1, then that means we have that this is going to be more negative. So for example, take negative. So if this is going to be negative, or take 2, for example, p equal to 2, then we would have 1 divided by x, the integral of that. So as t approaches infinity, it's actually going to go to 0. So for example, say p is equal to 2, then we would have this limit. So that'd be negative 1 divided by x. That'd be 1 to infinity. So as it approaches infinity, it's going to go to 0. And we would just have the limit here. So that's equal to just 1. So obviously it's converging. So as it gets more negative, or as the exponent is going to be negative, then that means the value here, as it approaches infinity, is going to go to 0. So that means this integral, x to the p, converges. So the cases are when p is between 0 and 1, or negative infinity to 1, the integral 1, or I could also put 1 inclusive. So we say that the integral from 1 to infinity, 1 over x to the p dx diverges. And the integral, so when p is in 1 to infinity, then this integral 1 to infinity, 1 divided by x to the p, converges. And this integral, we will see something related later in the future when we're talking about the sequences and series of numbers. All right. So it only converges when it's greater than 1, diverges when it's less than or equal to 1. All right. So now let's suppose that we want to evaluate an integral that is continuous on a certain region, but has a vertical asymptote at one of the boundaries. So in this case, we can evaluate the integral as much that we did as we did for infinite integrals. So, for example, there are 3 types. So we call this the type 2 integral now. So if f is continuous on a to b, where a is the closed and b is open, and it's discontinuous at b, then we say that the integral from a to b of f of x dx is equal to the limit as t approaches b from the left of the integral from a to t of f of x dx. So provided that the limit actually exists. And similarly for 2, but this time when we have a closed or a open and b is closed, so a is discontinuous at a, and we would have a similar expression. And so if f has the discontinuity at c, where c is somewhere between a and b, and both of these limits hold, so meaning that they're convergent, then the integral from a to b converges as well if both of these are actually convergent. Okay, so let's have a look at some examples. So we want to evaluate the following integrals. Okay, so we see that the integral here is discontinuous at 2. But what happens to the right of 2? So what we actually want is from the 2 from the right. So we say that the limit as t approaches 2 from the right of the integral from t to 5, 1 divided by the square root of x minus 2. So this integral here is actually given by, so the limit t approaches 2 from the right of 2 times the square root of x minus 2. And this is between t to 5. Okay, so that would just equal to, so 2 times the square root of 5 minus 2, subtract the limit as t approaches 2 from the right of the 2 t minus 2. Well, as if we put 2 in here, this value is just going to go to 0. So that means we would just have 2 root 3. So the limit exists. So that means the integral here, 2 to 5, 1 divided by root x minus 2 is equal to 2 root 3, meaning that it converges. Okay, so let's have a look at the second example. We have the integral from 0 to 1 of 1 divided by x squared. Note that from 0 at 0, the limit does not, the function is discontinuous there. So we have to evaluate what happens to the right of 0 here. So meaning we have to see what happens as we approach 0 from the right of the integral t to 1 divided by x squared. All right, so this integral we calculated before, to 0 from the right of negative 1 divided by x from t to 1. So we have the first value, which is 1 over 1. So I'll put that as negative 1. But for the second value, we have plus the limit as t approaches 0 from the right of 1 divided by x, or t. So what happens as t approaches 0 from the right? Well, we see if we draw the graph of this, as it's approaching 0, it's approaching positive infinity. So no matter what, we have, like, for example, -1 plus infinity, but obviously infinity is just going to be infinity. So that means the integral actually diverges, meaning that the integral does not exist. Okay, so that's the second example. Now let's have a look at the third example where we're dealing with 1 over x dx. So this integral as well, but we're actually going to break this up into two different integrals here. So from -1 to 2, we want to make sure that we're considering the vertical asymptote of 1 over x, which is at 0. So we're going to write this as the integral from -1 to 0 of 1 divided by x dx plus the integral from 0 to 1 or 0 to 2 of 1 divided by x dx. So only if both of these are convergent, then we say that this also converges as well. So let's try to evaluate the first one. So we're going to say, well, this is the limit as s approaches to 0 from the left of the integral from 0 to -1 to s of 1 over x dx plus the limit as t approaches 0 from the right of the integral from 0, so that's t to 2 of 1 over x dx. Okay. Now we compute this integral, so that's also going to be equal to the ln of x from -1 to s. Don't forget the limit as well. So we have the limit as approaches 0 from the left plus the limit as t approaches 0 from the right of ln of x from t to 2. So remember, only if both of these limits exist, then we say that the integral converges. However, as t approaches 0 from the left, so if I draw the graph of this, it will look something like this. So that's the graph of ln of absolute value of x. As it's approaching 0 from the left, it does not exist. So it does not exist as s approaches 0 from the left. Now similar, but for t here, we see that, well, it's also going to go to positive infinity. So we say approaches infinity as t approaches 0 from the right. So because that's the case, we say that the limit or the integral here does not exist. Or it diverges. All right. So let's have a look at one more example here. This one will be a bit interesting. Okay, so this is an integral that we calculated before as well, I believe. I think we did, yeah. But anyways, if we want to calculate this integral here is just done by integration by parts. So I'm going to use the DI method. I'm going to be integrating the 1, differentiating the ln. So that'd be 1 over x, and we have x here. So going this way and then this way, this integral just becomes x ln x minus x, and from 0 to 1. But one thing to note here, we're only interested from 0 to the right. So I'm actually going to write this as the limit as t approaches 0 from the right of x ln x minus x from t to 1. Okay, so that means for t equal to 1, or when x is equal to 1, so that just be 1 times ln of 1 minus 1. So that means this is going to go to 0, but we still have the negative 1. And as for the second term, we had the limit as t approaches 0 from the right of t ln of t and minus t, so that's going to go to 0. So the t here, as it's approaching 0 from the right, this is also going to go to 0. So I'll just leave that. So minus 0. Okay. Well, how do we actually evaluate this integral over here, or this limit here? Well, do you think we could use maybe, if we do a direct substitution, that wouldn't really give us any answers to it, because this is going to go to 0, this is going to go to infinity. So that one actually, so 0 times infinity is an indeterminate form. So that means we have to use another technique. Luckily, we could actually use L'Hopital's rule, because here, so we saw the negative 1, but I'm actually going to be focusing on this part here. So we have the limit as t approaches 0 from the left, right, of t ln of t. I'm going to rewrite this as the limit as t approaches 0 from the right of ln of t divided by 1 over t. Now, see, if you approach 0, we're going to get infinity over infinity, which is an indeterminate form. But so that means we could use L'Hopital's rule. So now, by L'Hopital's rule, we could say that, well, the limit as t approaches 0 from the right, so the derivative of ln of t is going to be 1 over t. The derivative of 1 over t is negative 1 over t squared. So that means we would just be left with negative of the limit as t approaches 0 from the right of t, which then goes to 0. So that means this limit here is actually going to be 0 based on what we just calculated. So in fact, the integral is equal to negative 1. So sometimes it's useful to use L'Hopital's rule if you're trying to determine whether an integral converges or diverges, especially when you're using integration by parts. It's very useful. Okay, so this is going to be the last part. So now let's suppose that we want to determine if an integral converges or diverges. We don't care if there's a value to it, because sometimes the integral is harder to evaluate. So we would use the comparison test to evaluate or determine if the integral converges or not. So it says that if f and g are continuous functions with f being greater than g greater than 0, and if we consider for a x greater than a, then we say that the integral of f of x is convergent. So if this has happened, then this is also convergent. If g of x is divergent, then f of x is also divergent. Okay, so let's say, for example, we want to determine if the integral from 2 to infinity of e to the power negative x squared dx is convergent or divergent. Well, this is actually a hard integral to compute, which basically is out of the scope. So we would actually have to use the comparison test. Well, here's the thing. For x greater than 2, we know that, well, x is going to be smaller than x squared. So multiply both sides by negative x squared and negative x squared. And now raise both sides to the e to the power negative x is larger e to the power negative x squared. Okay, so what happens to this integral then? So we have that this integral, so using part one, the integral from 2 to infinity e to the power negative x dx, we know that this integral already converges, which is just going to be e to the power negative 2, which means that it converges. So that means the integral here, 2 to infinity of e to the power negative x squared, converges as well. Although the value might not be obvious, we don't really care about that. Okay, so let's try this one. Determine if this integral, so 1 over x plus e to the power x dx, converges or diverges. So same thing, same style. For x is greater than 2, we know that, well, x greater than 2 then, it's also greater than 0. But if we add e to the power x on both sides, x plus e to the power of x is greater than e to the power of x then. And so if we take the reciprocal of it, x plus e to the power of x is smaller than 1 over e to the power of x then. So what we have here is a larger function. So we know that this integral, so that's going to be the same as this one here, it converges. So since the integral from 2 to infinity, 1 over e to the power of x dx converges, then so does this integral. Okay. So now let's have a look at the next one. So we want to determine if the integral from 2 to infinity of 1 divided by 1 divided by x minus e to the power minus x is convergent or divergent. Well, same style as before. When x is greater or equal to 2, we would have that, well, x is greater than 0 then, so x subtract e to the power minus x is still going to be larger than negative e to the power minus x. Then take the reciprocal of it, and we would have the opposite sign, dx. However, in this case, this integral here is actually divergent because, well, that's also the same as saying e to power negative e to power x, which we know negative e x dx diverges. So that means the integral from 2 to infinity, 1 divided by x minus e minus x, diverges. Okay, so one more example. We have the integral of 1 plus sine squared divided by x times 2 minus cos squared of x. Okay, so for x greater than 2, we know that the sign here is actually bounded between 0 and 1. So this is sine x sine squared of x less than or equal to 1. And we also know that 1 is less than or equal to 2 minus cos squared of x. And this is less than or equal to 2. So what that also means is if we add 1 to this side, we add 1 to this side, so we have 1 plus sine squared of x is greater than or equal to 1. But as for the bottom, we're only interested in this part here. So 2 minus cos squared of x less than or equal to 2. So if we take the reciprocal of this, get 1 divided by 2 minus cos of x, which is greater or equal to 2, or 1 over 2. Okay, so now we say that, well, 1 plus sine squared of x divided by x 2 minus cos squared of x. This is going to be larger than 1 divided by 2 times x. But since this integral, 2 to infinity, 1 divided by 2x, diverges, then that means this integral, 1 plus sine squared divided by x, 2 minus cos squared x dx also diverges. And actually, one mistake I made in the last example, this should actually be larger still, I think. Let me double check this. Yeah, so this is actually should have been larger here. So that was a mistake here, but the integral still diverges. Okay, so that's going to wrap things up for today. So that's all for the integral section. So I think the next lesson we will actually be having a look at starting the applications of integration. So if you have any questions, just feel free to let me know.